Hello, everyone. I guess we'll go ahead and get started. Um, so welcome to this week's session of the spring semester RC seminar. We had a few changes to our presenters sort of last minute. Um, so I guess we'll have one presenter this week. Um, uh, Remy, are you ready to present?
Yeah, sure, no problem.
Great. Then we'll go ahead and start with our presenter, Remy Al-Ajrodi.
Yep.
Please start sharing your screen and begin your presentation whenever you're ready.
Just a second.
One presenter?
Yeah, it seems that the other two presenters today let me know that they would not be able to make their presentation.
Okay. But I heard that in the email, Ponson will be doing it on 18th of July.
Yes.
And Kansan was planned for today, right?
Yes.
So Kansan, are you there? Why?
Yes,
Yeah.
Uh,
What happened?
I didn't know by today I have my presentation today. So
Okay.
yeah, did you
Do you think you can do it
inform me?
on 18th? Yeah.
Yes, that's okay.
How many presenters do we have on 18th?
3, but we can make it 4.
Ah. Okay. Okay. We need to think.
Mm.
Okay. Let's start.
Yeah.
Can you guys see my screen?
Yes.
Okay, perfect. Just a moment. Okay, so hello everyone. So if you are wondering whether it's possible or not to reproduce, interpolate, and also extrapolate the dynamic of a system, so basically the space trajectory over time, you probably should read and understand the paper that I'm about to present today. So it's titled Learning the Dynamics of Coupled Oscillators from Transients, and it has been written by Huawei Fan et al. So once settled to the asymptotic attractor, for example, a steady state, many information of the system dynamics will be lost, and transient dynamics may allow to retrieve useful information to interpolate and extrapolate complex nonlinear dynamics. So they want to try using the transient time series of a system to replicate its entire dynamics. However, there are some challenges with reservoir computing for learning the dynamic system. So first, we would need to find all the non-attracting sets and their unstable manifold. And second, the models of the systems are usually unknowns, so the mathematical models. So we have to develop a model-free database techniques. So usually the RCs, they are trained using measures from the asymptotic dynamics, so stable states, that the systems are finally developed to over time. So here, the problematic of the paper is this. Based on the transient time series measured at several states in the stable regime, can we predict the critical points where the system becomes unstable? So there are like many problems. Generally, the smaller the perturbation, the larger the perturbation, the longer will be the transient. And the smaller the perturbation, the shorter will be the transient. So transient dynamics are usually short in comparison to asymptotic dynamics. although time series has to be long to train RC. And the transient dynamics, they are dependent on the initial conditions, the perturbations magnitudes. So the aim of the paper is this: for bifurcation scenarios in coupled oscillators, so basically numerous oscillators that are coupled to each other's in their equations, the machine trained by the transient time series acquired in the stable regime is able to predict not only the system evolution in stable regime, so over time, but also the critical point where the stable state becomes unstable. So let's talk a little about the protocol here. So we are talking about parameter-aware reservoir computing. So these diagrams show the RC structure with two inputs. So the first one is called U beta because it's a time series dependent on a parameter, bifurcation parameter called beta, and the control parameter, which is the second input that we feed into the reservoir, which is the beta parameter. So that's why we call it parameter-aware reservoir computing. So the key equation of the reservoir state's evolution is given here. So we have RT plus delta T equals to the activation function, which is a tangent hyperbolic, times A, which is the weight of the reservoir, times the R matrix, which are the reservoir states, plus the weight input times the time series input, plus beta, so the bifurcation parameter, times the bias vector. So on the right, you can see the model's hypers parameter. So we'll see that later for each of the cases, and the dimensions of the matrices. So when they wanted to train the reservoir, they used what we call the ridge regressions. So the purpose of these regressions, for example, in difference with the traditional regression, the mean square, for example. So it's a method that allows to improve ordinary list mean square by adding what we call a regularization term eta. So as you can see, eta is a factor of the W out's weight matrix. So it means that if eta is very, very low, when we minimize this cost function, basically, we will not have to minimize W out because eta times W out will be very, very low. So we'll have to minimize U minus W out times V. And note that the matrix V contains the new reservoir states for each sampling time, as you can see in the yellow square. And this is called new reservoir states because it takes the reservoir states, and if it comes from an odd node, it simply is the same reservoir, the same states. But if it's an even node, we put it at square. So basically, they use this to increase computational capabilities. And why is the ridge regression effective? Because at the end, as you can see at the end of the development, so basically we have to derive this function. So since it's a square function, we have one minimum. And then basically we find this for W out. And as you can see, we have V times V transpose. So this is a positive semi-definite matrix, which means that all eigenvalues are non-negative. And since we add plus eta times identity, this matrix is for sure inversible. So it's numerically more stable than the ordinary linear regressions. And as I said before, the eta parameter offer trade-offs between fitting the training data and the model, allowing model generalization if it's much bigger. So this was for training phase, right? So when we finish the training phase, we don't have inputs anymore. We just have the parameter as the bifurcation parameter as inputs. So So now we will replace the input U beta by the model's own output V from the previous time state. So it would be Vt minus delta t. There's a little mistake here. So basically, this is a feedback loop. So the reservoir state update equation at the bottom here, it changes, and it becomes the activation function time the reservoir weights time the reservoir states plus W in times the output of the reservoir plus beta B, with the output of the reservoir V being equal to the output weight matrix times the new reservoir states. So for the first experiments, they use this hyperparameter. So yeah, basically they used 5,000 nodes and like sigma equals to 1. So basically it means that bias inputs and the W in weights matrix and the A matrix are uniformly randomly generated from minus sigma to sigma. And yeah, spectral radius of 0.1 and eta 10 times 10 to the power of minus 1. So so now we are talking about the results that they had. So the parameter aware reservoir computing was tested on 3 different systems. So the first one, which we're going to talk about, is the quorum sensing in coupled Stuart-Landau oscillators. We'll see this in detail later. Then we'll talk about the amplitude death in coupled Stuart-Landau oscillators. And finally, complete synchronization in coupled chaotic oscillators. So we'll see this in detail now. So what is quorum sensing? So quorum sensing is the phenomenon where a population of coupled elements exhibit a sudden transition from individual to collective behavior when critical population density is reached. So here the population density is called rho. So for example, we could make this analogy. So imagine like we have mechanicals metronomes. So, you know, the ones that beats, and we put it over metal plates. So if they are very far away from each other, they will not influence each other. But if we take it very close to each other, they will influence each other through what we call the medium, which would be the metal plates. So at the end, they will all oscillate in synchronize. Yeah, so as you can see, there is 2 equations. So the little zj dots, which represent the evolution of the dynamics of the Stuart-Landau oscillators, which are coupled to an external medium, which is represented by the large z variable. And this large z variable has also its dynamics, which is tied to the oscillators, as you can see. And then there are 2 other parameters. So, sorry. Yeah. So RZ, which is the mean value of all the ZJ. So here we have 100 oscillators for this first experiment, and we take the mean value of all of their values, and it's called RZ. So then we have R, which is the mean value of the medium over the period of time t. And for their case, they took the 100, so yeah, 100 oscillators, what we call the diffusion coefficient D equals to 1.5, which is basically the coupling strengths between the medium and the oscillator. And then the natural frequency omega 0 equals to 1, and what we call the relaxation parameter J equals to 0.2. So yeah, J it represents like how quickly the medium will return to its equilibrium states after being perturbated. And yeah, so yeah, so this I've already talked about it. So the hyperparameters that they used for these experiments. So basically, an R, a reservoir of 5,000 nodes, a sparse connectivity of 0.1. Yeah, so yeah. And maybe I should mention like the dimension of the matrix weight input is 2n plus 2 because we have n oscillators, and each oscillators it has, as we can see here, the ZJ, it has an imaginary part and a real part. So the input will be a vector of 2 with the real part and imaginary part. So that's why we have 2n plus 2. So what did they have for results for these quorum sensing experiments? So the goal was to predict the quorum sensing transition. So as we have said, is the critical point where the system switch from the quiescent, so basically a stable regime, to a synchronized oscillatory behavior. As you can see, it happens at rho c equals to 0.38. So yeah, so they will use the transient data from the quiescent regime to train the model. So what they mean here is basically they will like train the RC using the row in the vertical lines. So 3 time series that they concatenate each time so that then they can feed the reservoir. And each time they compute the R for each of the row, there is a transient before the asymptotic behavior. So these transients will contain informations that will allow then, after the training, the reservoir to reproduce all of this all of this behavior. So yeah, so as you can see here, the RZ is plotted. So this is the model that the RC will hopefully be able to reproduce. So the R here, it's measure the synchronization among the oscillators. So when the when the R is 0, it means that there is no synchronizations among the oscillators. So basically, as you can see, it's for a density rho, which is very low. So that would mean in our analogy that the metronomes are very far away from each other. And when the density increase, so since the oscillators, they are 100, it's a fixed amount. So it means that we would reduce the volume of the experiments. So we would like bring the metronomes together. So they will influence each other over time. So that's why you see that the oscillation increase with rho, that when rho increase as well. Yeah. Oh, sorry. So then this is the time series that they have. So you can see that they use different value of rho. So 3 values, 0.3, 0.32, and 0.34. So this means that it's way before the bifurcation points, because as you remember, the bifurcation for this equation is 0.38. So they trained the reservoir computing only with quiescent regime, so before bifurcation. And each time they trained it with over a period of t, which is equal to 200 time units. So they didn't precise the units of time. So yeah, as you can see at the right, this is the predictions time series. So as I said previously, we have the imaginary part and the real part for the z equations. So x is the real part. And yeah, so they plotted like 5 predictions with 3 beings already learned by the reservoir. So yeah, so and also 2 new values for rho, so 0.36, so still before the bifurcation point, and then rho equals to 0.40, so after the bifurcation points. So the results that you can see in the C panels at the right, so they show that the parameter where RC, the reservoir computing, is able to accurately reproduce the dynamics for both the training data, so the first 3, and the unseen data, so the last 2. As you can see, for the 0.36, it can very well predict that this is a stable quiescent regime, so it will find the oscillations will be gone over a period of time, while for the rho equals to 0.4, so after the bifurcation, it's accurately predicted that the oscillations will be maintained over time. So yeah, the model has an ability to capture the underlying system dynamics and predict the critical transition to synchronized oscillations, even without being exposed to the data from the oscillatory regime during the training. So so now the article was more specific to the entire system, unlike the previous figure, which was mainly focused on individual time series. So these figures, it shows how the RC predicts the evolution of the parameter RZ and R, which are related respectively to the oscillators and the medium. So these are the average values that we've seen previously. And each time it's plotted the final, so the asymptotic value over time. So for each row, so this is basically a bifurcation per diagram. So the control parameter rho is gradually increased from 0.3 to 0.5 by a step of rho equals to 0.05 for each time. And yeah, so the machine is run for a period of t equals to 1,000 units of times. Again, no units, they didn't mention it. And then they calculate the outputs time average parameter RZ and R for a period of t equals to 10,000 units of time. So we can see that the machine predicts accurately the critical population density. So it happens at rho C equals to 0.38, even though that it hasn't seen it during the training. So the training are like the vertical blue values for rho that you can see. So yeah, this is good predictions. And as I mentioned in the introduction, if you use the transient dynamics to train in reservoir computing, you have to have a good amount of data, right? Because if the transient is very low, you will have very few information to feed your reservoir to train it basically. So they have showed this plot, which is very interesting because it showed the relation between the delta, which is the perturbation that they use on the equation. So the larger is the perturbation, the longer will be the transients, and the shorter will the shorter will be the transient, the little will be the perturbation. So yeah, so as you can see, the horizontal lines here, they are the simulated values of R. So these are the model values. So this is the target. And you can see that as the perturbation is increased, the RC can basically reach more closely these values. So the prediction performance is improved by adopting more sampling states. So when we have more data points, the RC can after predict more accurately the dynamics. So yeah. So now let's talk about the second experiment, which was about amplitude death in coupled Stewart-Landau oscillators. So this time, amplitude death is defined as the cessation, so the stop of the oscillation in coupled oscillators as the system bifurcation pass through a critical value. So basically, it would be the inverse of the previous experiments. So previously, when we increased the bifurcation parameter, the coupled oscillators started to oscillate. And now it's the inverse. So when we will increase the bifurcation parameter, the oscillations will stop. So to be able to generate amplitude death, we need to have a parameter mismatch. So as you can see, we have two oscillators, and the natural pulsation omega is different from each other. So for the first one, we have 2, and for the second one, we have 7. And then we have the coupled strength parameter, which is called epsilon, as you can see here. And this, so this shows how the two oscillators are coupled to each other. And this is the bifurcation parameter. So, so now we will use this parameter RC. So basically, it's the same configuration, right? So the only difference is the hyperparameters. So they change the nodes, they decrease it very largely, so from 5,000 to 6,000. And the parameter eta has decreased also a lot. So, has increased, sorry. So it could lead to less computational time and more generalization of the data. So now we'll have two inputs for the training phase. So the coupling strength epsilon, so the beta here, it's the epsilon now, the bifurcation parameter, and the training time series. So they generated and combined, so 3 time series for the data set, so for 3 different epsilon, and the length of the time series for each time, it's like 6,000 data points. So as previously, the initial states of the oscillators. So when we first start at t equals 0, the initial states, they are chosen randomly, uniformly from the range -1 to 1. So sigma still equals to 1. And the time step used to the simulation is 0.02. So here, the bifurcation parameter is epsilon, and at epsilon equals 1, the bifurcation point happens. So this is a little plot so that you can see how the system evolves for 2 cases. So when epsilon is inferior to this bifurcation point, so 0.8 at the left of the figure, you can see that the bifurcations, the oscillations are maintained over time, because as I said previously, so now it's the inverse. As we use epsilon larger, we will overcome the bifurcation point, and then we'll have no more oscillations. And as you can see on the right figure, when epsilon is equals to 1.15, so basically over 1, the oscillations, they get extinct over time. So yeah, we can see that they cease over a period of time of t equals to 20 times units, as you can see in the plot. So the bifurcation happens also if the delta omega, so the difference between the 2 pulsations of the 2 oscillators, are larger than 2 times the root square of 2 epsilons minus 1. So these are the 2 conditions. And again, the Z, they have real parts and imaginary parts. So in the inputs, U beta is a vector of 2. So to have a global picture of what happens to the system, they plotted bifurcation diagram. So the variation that you can see in the bifurcation paragram is the local extrema of x1 with respect to epsilon. Local extrema, so local minimum and local maximum. So each time they plot the time series, they take the local minimum and local maximum after some period of time. So yeah, so now you can see what is amplitude death as the parameter get bigger, then we have no more oscillations. So they used 3 epsilon to train the model. So this is what you can see with the vertical lines. So they use the epsilon equals to 1.05, 1.1, and 1.15. So this is in the quiescent regime. So when there is no oscillations again, and each time they will take the transients, the transient dynamics. So when they start the computation of the equation, they have the transient dynamics, and this is what they will take to train the RC. Again, it's the same. So now they want to know if they can predict the critical points where the system survives from amplitude death with few training data. So this is what they have for their predicted time series. So as they said in the article, this is very accurate. So yeah, so this is the bifurcation diagram predicted by the machine. So it was able to predict the whole dynamics using only the quiescent regime. So this is very interesting as a result. So now for the last experiments, the goal was to predict transition to complete synchronization. So the point where coupled chaotic oscillators start moving identically. So what we mean by chaotic oscillators, for example, it could be the logistic maps or the Lorentz oscillators, the 2 examples that we will see now. So they will use only transient data again from the synchronized regime. And this approach will aim to predict this time the desynchronization from the synchronized states. So it's always the same way of proceeding. Yeah. So now the difference is that they will focus on chaotic systems and prediction of desynchronization rather than synchronization. And they will use data from synchronous states to predict desynchronous states. So this is the equation of 2 coupled chaotic logistic maps. So as you can see, again, epsilon is the bifurcation parameter. And it basically shows the coupled strengths between the 2 chaotic logistic maps. So again, this is the same parameter RC, but the hyperparameter changed. So they again decreased the reservoir nodes from 600 to 100 this time. The sparsity of the reservoir is still 0.1. So that means that each node is connected to approximately 10% of the other nodes. Sigma, so for the uniform distribution, still 1. And lambda, I think it has decreased. So maybe they they wanted to reduce memory retention, but they didn't really specify why they chose these parameters. So basically, they just run a function on MATLAB, which is an optimizer. Yeah, I don't remember the exact name of the optimizer, but this is what they cut at hyperparameters. So this time again, they combined 3 different time series for the data sets, and so the time series in total was 10,000 data points. So these are very important information because transients dynamics, they have few data points. Yeah. So, so first for the logistic map, so here are a few time series. So to measure the degree of the synchronization, they use the synchronization error. So basically they take the two time series and they subtract them and they take the absolute value. So basically what it means, it's if this delta x is equal to 0, it means that the two time series are identical. So the system is in complete synchronization. And if delta x is positive, it means that there is the synchronization. So for interpretation now, we can see that when epsilon is above the bifurcation point, which is a critical point of 0.25 this time. So the system will be in synchronization because, as you can see, the average delta x will be 0. So yeah, in the figures, the first A and B, they are the respectively the training time series. So we have 3 time series, always the same. For epsilon equals to 0.26, 0.28, and 0.30, so above the bifurcation points when there is full synchronization. And then they want to predict desynchronization this time. And as you can see on figure C, so this is the variation of the time average synchronization. So basically the average of the synchronization delta x over a period of time t. And the black square is the model and the RC is the prediction. And you can see that the prediction is very well, very, very accurate. So they did the same experiment now as the logistic map, but with the Lorentz oscillators. So again, a chaotic attractor. So the two oscillators now, they are synchronized, not when epsilon equals to 0.25 as here, but but when epsilon equals to 0.42 this time. So they trained again the model with three different sampling parameter. So epsilon equals to 0.5, epsilon equals to 0.55, and epsilon equals to 0.6. Yeah, so the initial conditions still, they are randomly chosen within the range of -1 to 1, and the system is evolved for each point over a time step of 0.02. And you can see that the synchronized error is, it gets to 0 for each of the time series over 60 period of time. And the RC model is not quite accurate. However, it can still predict the bifurcation points. Yeah, so this is what they used for hyperparameter. Again, they used the same MATLAB function optimizer. And yeah, so the RC was able to predict the critical coupling at epsilon equals to 0.42, 0.43 approximately, but it was less accurate than the other models. Yeah. So these are additional findings now. So these findings, they revealed that the prediction performance was worsened when they use larger sampling parameters, so larger rho or epsilon here. And for example, they didn't show the results, but they just mentioned it. So for this experiment, which was the logistic map that we've seen earlier, when they used larger sampling parameters as training data, the RC was not able to predict the bifurcation points near epsilon equals to 0.75. So we cannot see it here because they didn't show the picture, but it would be like in the left of this picture, there would be other bifurcation points, like period doubling, bifurcation. And so this failure was due, they attributed it to the fact that they had a very short transient time series, so above a period of t equals to 15 time units. And as we said earlier, usually the RCs, they are trained over hundreds and hundreds of times units. So this is very few. So that's why they explained that the RC was not able to predict. So such brief transients, they don't provide sufficient information about the system dynamics for the machine to predict the transition accurately. So yeah, so this observation, it also aligns with the findings from the quorum sensing, the first experiments, when we saw that the prediction performance was gradually deteriorating as transient lifetime shortens. So this is what we've seen here. When the delta was little, the prediction was very bad, and the more we had transient dynamics, so the more we had points to train the system during the transient dynamics, the more accurate was the RC. Yeah. And so to conclude, the transient dynamics data, it allows to predict the phase transition in complex system using the reservoir computing. It also works with a few data points, but not too few, otherwise it will not be able, of course, to predict. And it's also possible to predict the critical point, so the bifurcation points and the system behavior overall in unstable regimes. And finally, it's still they still have open questions regarding the generality, sorry, of these findings and the relationship between transient lifetime and prediction accuracy. So that's it for me. Thank you very much for listening. And if you have any question, I will try to answer them.
All right, thank you for your talk. Do we have any questions from the audience?
May I ask you a question?
Yeah, sure.
Thank you very much for your great talk. And could you show the page 25, complete synchronization coupled Lorentz system?
Okay.
Yeah, and so my question is, what is the training data in this case?
Oh yeah. So the training data, it would be the Lorentz equation. So as you can see here, we plot the X time series. So the training data is this X.
Did they just show the difference of these two systems?
So you mean, did they use the delta X to feed the reservoir?
Yes, exactly.
Oh yeah. So I don't want to tell you because I'm not sure. So
Oh,
I don't want to say something false. So I'm not sure about this one.
I think the input is difference of the two systems.
Yeah, it could be.
Because
It could be.
because the ecosystem network itself is not chaotic in this case, right? Because I remember that the spectral radius of the system is very small.
Yeah,
Like,
it is very
yeah.
so it's very stable. But what I mean by chaotic is the Lorentz attractor is a chaotic system.
That is very interesting to me. Like even if the elements of the coupled system is chaotic, we can by focusing on the synchronization of the two systems, then we can predict the critical point
Yeah.
of the synchronization.
Yeah.
By using with non-chaotic or non-chaotic ESN, because
Yeah.
it is very easier, much easier. I think it is much easier to set the hyperparameters the ESN, because we just have to make this spectral radius smaller.
Yeah, but why would it be easier?
Easier than the setting the hyperparameters to predict the two chaotic systems.
Oh yeah.
Which is non-coupled.
Oh yeah, for
Mm.
sure. So that's why they could
Mm.
have less computational resources. So they used very
Great.
low nodes.
And
Mm.
okay. Yeah. To be
Yeah,
honest, I wanted to know the delta x is just is only for the x coordinate or the all the coordinates.
so
Yeah.
they only showed this picture as a result.
Mm.
So I guess they could do the same with Y and Z as well.
Ah,
But this was
okay.
the only result that they show. So
It,
yeah.
it might be possible to conduct the similar experience
Mhm.
only by showing the x coordinates difference.
What do you mean?
I mean, if do they if they show the all differences of the two, I mean, two systems, I mean, the x and difference of x and y and z coordinates, then we might be possible to get the similar results even if we restrict ourselves to the difference of one coordinate, like x.
Oh, so you
The
mean like
only
they would drive the ESN with delta x and then y and z?
mm.
Oh, so uh, I don't know
we
because
mm.
they really didn't mention this, but
ah
if this is like
but
an open question,
mm.
I don't know because delta x and y and z
ah
are not so correlated, but maybe this would provide more information to the ESN
mm.
process, so it would be able.
Yeah, if we consider the delta x as a variable of dynamical system of this coupled system, then based on the Tarkin's theorem, if the ecosystem network has memory, then it might be possible to get this similar results, even if we only use the difference of the x coordinate of the two systems.
Yeah, maybe.
Mm.
Because actually this is maybe what they've done. So I don't know if they didn't precise it or if I didn't see it, but so yeah, so I need actually to see this because I don't
Yeah.
know if they use X or delta X as driven inputs. So I'm sorry
Mm.
answer actually.
No, yeah, that's great for to discuss with you. Thank you very much. And can I ask the other question
I
as
think it's
well?
better that you at first check the paper,
Sorry?
the setting.
Yeah.
It's better that you at first check the setting in the paper later.
Yeah,
And then,
yes.
yeah, the point that you mentioned, so Terasaki-san mentioned is important that, for example, delta X, because to predict the next state of delta X, if Y and Z was involved, then anyway, equal-state network should have these terms inside, right?
Yeah.
So yeah, so it's definitely about the Tarkin's theorem.
Yeah.
So yeah, that's the point.
Yeah,
So
thank you
what's
very
your other
much.
question?
Yeah, so my question is about the other question is about the things on page 15.
15.
Yes. Yes. And I think they mentioned about the influence of the transient to the prediction of the critical points of the synchronization, I think. And the graph from this graph, it seems like it will get saturated by as we increase the scale of the transient, right?
Yeah.
So do so do I think it depends on the system, but the curve keeps increasing if we extend the
I actually had the same question. I don't know because they didn't provide this information. So I would have liked to see what happens after one, you know? So
yeah, but
I don't know.
If you consider, for example, a logistic map,
Yeah.
then yeah, for a certain bifurcation parameter, then it will exhibit some kind of transient, and we might be able to conduct the similar experiments with the logistic map. But in that case, if the state of the logistic map go outside of the interval 0 to 1, then it will go to minus infinity, right? So it depends on this system. Like in that case, the too much if we take this delta too much bi bigger, then the system will break down. So I
It
think
could
yeah.
lead to instability maybe. So if
So
the
it might
perturbation,
depends on the fate, the
yeah.
dynamics of the target system, but
So maybe if the perturbation is too large, the ecostate network would lead to instability and not be able to predict the dynamics also. So this is unfortunate that they didn't provide much larger amount of information. They stopped at 1, delta equals to 1. So
yeah,
we don't know.
yeah. So I think we to yeah, I think I think it depends on the target system. So we need to conduct the experience
Yeah.
corresponding to the target system. Yeah. Anyway, yeah, thank you very much.
Thank you. Thank you. So is there any question?
Yeah, I have a question.
Yeah.
Yeah, thank you for your great talk. And I want to know the significance of training transient dynamics for this prediction of critical bifurcation point.
Yeah.
And is there any comparison between training only transient dynamics and training only stationary dynamics?
So first I'll answer. So your question is like, is there any difference between training the data with this transient dynamics or training it with oscillatory regime, right? Like the difference between quiescent regime and oscillatory regime.
Yes, after transient, such as dynamics on attractor. Yeah.
So if you train it only with asymptotic values, basically
Yes.
you have no information to provide your reservoir computing with.
In the case of fixed point, yeah. Yeah, you say that if case of if the case of attractor is a fixed point after transient, there are no information.
Yeah, exactly. So your RC will not be able to predict the dynamics. There would be no information. Yeah.
Okay. Yeah, but in general case, it depends on system, I think. Yeah. If yeah, okay.
No, I don't think so.
Oh.
So it's different. If you're talking about the quiescent regime, which they use here, but in the quiescent regime, they took advantage of the transient parts because this contained many information to provide the RC with. So this is why it is valuable. However, it's very short. So as you have seen in the last slides, when I mentioned the additional results, they mentioned that they also used very, very short transients. So basically mainly asymptotic values. So in this case, the RC was not able to predict anything because there was no information contained asymptotic values.
Yeah. Okay. Thank you for your answer.
Yeah, sure. Thank you.
Are there any other questions? Okay, if not, I'd like to thank our speaker.
Thank you.
Yeah, and since there aren't any other talks this time around, we'll go ahead and briefly share my screen. Yes. So next week we'll be having our special session with Dr. Takamasumi, talking about reservoir computing with structure-controlled neuronal networks. It's important to note that this session will start at exactly 7, and in addition, we will be using a different Zoom link for the special sessions.
Yes, so external members will come.
Yeah.
Not only the internal members. And it's official.
Yes.
Okay. By the
Okay.
way, so 18th of July is the final day of this seminar, right? And we
Yes.
have four presenters. How shall we do?
We, I mean, we
So
could.
yeah, I mean, maybe, so yeah, it says Nakano-san is presenting, right?
Mhm.
But maybe he already is this the first time this semester, or
Yes.
it's the first time? And Nishida-san's paper is about this recent chemical reservoir computing, so it's important.
Yes.
Hwan-san, for his training, it's important to present, and it's related to the special session. This one is the paper he is going to present is about brain organoid,
Yes.
published in Nature Electronics. So this is also important and related to the special session. And I think Kan-san should have presented today, I think. I mean, and what he's going to present is also important for our research. And Nakano-san's work, Nakano-san is going to present which paper?
About ADFA.
ADFA. Oh, really?
Yes.
We haven't read ADFA paper yet. I
Yes.
didn't know that. I think Zan-san had presented. No? He hasn't presented ADFA paper. So okay, ADFA paper is also very important. Okay.
Yes. Of course, Fan-san already presents a paper about ADFA, but the paper which I will present is more, what should I say, fundamental.
That's DFA, not the ADFA. Maybe.
Sorry.
Okay,
DFA.
okay.
Yes.
DFA, applying DFA
Yes.
to deep neural network. One possibility would be, because that was already included in Zhang-san's presentation about ADFA, maybe we can skip if it is okay. What do you think, Nakano-san? Did you want to present? If it was not too much work, then it's okay. But if it is, but it takes time, right, to prepare.
Yes. I think it's okay for me, but what do you think? It's okay for me.
まあそう言われますよね。そうなりますよね。まあでも、カンさんはやっといた方がいいでしょう。で、カンさんが読む論文はまあ、みんな知っといた方がいい論文でしょう。なので、ただまあ、中野さんの内容は、おそらくザンさんが発表したのに含まれてますので、大変ありがたいのですが、今回はスキップということにしましょうか。
わかりました。
はい。じゃあ、西田さん、ファンさん、カンさんでいきましょう。
すいません。
はい。
一応そのスライドの方が、その応用例以外はできていて、そこ以外ならできるんですけど、 ちょっと応用のところだけまだ間に合ってないっていう感じなんですけど、なんか、それでも大丈夫だったら、ちょっと最後までいけてないので、えーどうしようかと思っているんですが、
応用例ってのはどういうとこですか？ナルマ10とか？
そうです。
あ
アルマテンとエコセットネットワーク
あ、
と、
い
あ
ろんなディスト
と、
リビューションでとか、
はい、バイオ神経系
バイオ、
ですね。あ
あった
った方がい
方がいい、
い気は、
あった方
そうですね。
がいいな。
はい、そう
あ、
です。
しかも、まあ、7月11日にそのバイオ細胞系レザメ使いますって話なんで、
はい。
あの、それが事変のキャパシティで特徴付けれましたとかは、まあ関連してるっちゃしてるので、
なるほど。はい。
はい。
わかりました。
はい。じゃあ18日はしっかりやっていただければと思いま
はい。
す。はい。
ありがとうございます。
で、ファンさん、ブレインオルガノイド。西田さん、ケミカルレザバーコンピューティング。はいはい。それでいきましょう。Okay. So we have three presenters. カンさん。So 中野さん、is not presenting this time. カンさん、and 西田さん、and ファンさん。
Great.
Okay.
Cool. Schedule has been updated. All
Okay,
right.
then see you next week.
Yep.
Thank you very much.
See you next week.